Hello and good morning. Today I'm going to present Lab 4 Laplace transformation for PGT205 signal and system. Okay. The laboratory require us to perform Laplace and inverse transformation, describe concept of zero and poles of a system, and ability to determine transfer function of system and plot of allocation of the pole and zero on X domain. Okay, let's go to the question. Okay, this is the first question: is to obtain Laplace and inverse Laplace transform for the following equation and transfer function. Okay, I have done it first. So this is the first question. Okay, first question is trace the sine 5t, which is written here, and the system is in the t or time domain, so we use sys symst to make as a variable for the t, and then we do Laplace y to do Laplace on the equation that we have defined on the line 6, and then we make it pretty using fs. Now let me show you by running the section. Okay, here on the right you can see that fs is equal to 3s divided by s squared plus 35 and square, and then by using pretty we get the equation like this. It makes it prettier and easier to read, which is 30s over s square plus 25 square. And for the question B, we also repeat the same step in time domain. We put the equation and do a Laplace again. And here we can see the equation getting pretty. Also the same for question C. Question D is already in Laplace, which is in 4 over s plus 3 in signal domain. So we use inverse Laplace to get the equation. So we run equation and we get 4 times exponent pretty, and pretty will arrange it to look easier for us to read. Question E is also the same, which is 4 over s plus 3 square, and the section we get the equation, and also f is also the same. Okay, now let's move on to question 4.2, which is to obtain the value of partial fraction in MATLAB. Okay, as usual, I use clear NCLC to remove all the data from the previous lab and clear the command window first. Then I set it to as a variable fraction since s is in s domain like in the question, and then we define the variable a and b, which is the numerator and b is the denominator. So we look here is s square minus 16, which is 1 for s square, 0 because the s power by 1 doesn't appear there, so it's 0, and then we put 16 for s power of 0. And then we do the same step for the denominator, which is s power of 3 is 1, s square is 8, s is 24, and s0 is 30. And then we proceed by using TF, a transfer function for the numerator and denominator, and then using residue RPK, R is for 0, P is for pole, K is for gain. Okay, and we put the data in there, and then we define this as ZBK is 0, pole, and gain. For the for the transfer function. Okay, I run now. We can see that the function has been written correctly here, and then the RPK value has been put inside, and then the sys is converted to contain zero tupole gain model, which is simplified into two, the denominator simplified into two equations, so we can easily move it if we want to. Okay, the second is also the same step. We run and we can see that the system convert its complex function into a simpler one, and then 4.2c is also the same. Okay, now let's move to question 3, is to obtain the pole and zero of the Fourier transfer function and plot the system using pole, zero, plot, and plot the system magnitude response using MATLAB format. Okay, just like before we do in question 4.2, there's a numerator and denominator for each question. So we do as before. Oh, wait, this one I missed a 0. Okay, x power 3, x power 2, x power 1, a 0. Okay, now it's correct. Okay, now firstly we do the transfer function first for numerator and denominator as before, and then we convert it to a zip, put the transfer function into a zero pole gain function to get the value to plot on the graph. Then this is, we make a figure, one figure for zero pole graph, and then this one you make a figure 2 for plot, which is for the magnitude. Okay, now let's run the section. Okay, now as we can see here, this is a zero and poles graph, which has been using the ZPK and been plotted here, and this is a figure, magnitude figure, which is a board diagram from the board plot. Okay, question B. So repeat the same step, but this one I already done the calculation, which is why we need to combine all of this bracket into one, which will get s power of 3, 13s square, 3s, 32s, and 20. They've been expanded. So then we do the transfer function, ZPK, and figure and plot the zero and poles. You can see here, there's only zero. This is a pole, and I don't see this any zero anywhere. This is the matrix diagram, which is going down. Then for question C is also same step. Okay, this one got the zero and poles here. Then this is the magnitude. Okay, now moving with reference to the question 4, with reference to Laplace transform table, transform the transfer function equation. Okay. For question A is s plus 3, s power s cubic plus 2, 7 s square plus 10s. Okay. Okay, firstly, we need to break this into a simpler form, which is here. If we expand it, we'll get the same number back by using, you can easily get this equation using calculator. Then from there we can break it into three: s, s plus 5 and s plus 2. Then we get all this equation here. Then each of this equation will be timed with all of this. Okay, so from there s will cancel this s, so we get s plus 5, s plus 2. And then here is s plus 5, so it we cancel s plus 5 here and then get s plus 2. And also for c, s plus 2 we cancel and then we get s plus 5. Then from there we need to expand the a first, because we got two equation here, make it become 1, and then we can compare coefficient down here. So for a is we take s square first and then we look for the equation with s square. It's 1, 2, 3. And then we also need to look here, s plus 3. Okay, for a we can see there's no s square here, so 0 equal to a plus b plus c. For s1 got 7, 2, 5 and s here, so 1 equal to 7a plus 2b plus 5c. And for s0 we got 3, 10, and that's it. There's no other s power by 0, so we get 3 equal to 10a. So now we can easily get a by moving 10 over 3, so we get a equal to 3 over 10. And then for s2 we can get 0, a plus b plus c, so we can get b equal to minus a minus c by moving it to the other side. However, we start here and we need to make equation s1 first. Okay, from here we already got value of a and b, so we can replace it in here, a and b. So we left with only just a, c just now, because we also can replace this, so we only left with c here. So now we get negative 2, 3 over 10 minus 2c plus 5c equal to 1 minus 2 over 10, which is has been moved. This one move there, and then 3c equal to negative 11, 10 times 16. Then let's see, we get c. After we get c, we move it to the second equation that we made, and then we get d. Okay, from there we will replace the value a, b, c from the equation that we done first, which is this one, and then we move all of this outside of the Laplace, which we will do later here. And then from there we look at the table, and 1 over s is equal to 1, and this one 1 over s plus 5 equal to e negative 5t, and negative 1 over 6, 1 over s plus 2 is equal to e exponent negative 2t, 1 over 6. Okay, That's for question A. Now let's move to question B, which is simpler than question A. It's a direct. It gives you equation, so we can just split it into two, just like before. Then repeat the same step. Time the numerator only before, and then we get the equation below, and then we take out the S1 and S0 for to compare our coefficient. Then we get the A is 1 over 5 from this step, B is 39 over 5 after replacing the A that we got earlier. Then replace it again from the first equation here, SS A plus B. Then we move the numerator outside, so we can get a value to compare in the table, which is 1. Then we get 1 over 5, 1 over s is 1, and 39 over 5 exponent equality, which is 1 over s plus 20 after Laplace. Okay, that is for question number 4, and we are done with all the lab question here. Okay, now let's go to the discussion. Okay, by using MATLAB, we can get Laplace, and when using Laplace, we can get the Laplace equation by using the command Laplace x and I Laplace x. X is any number, and then it can convert it for us without difficulty, just like this. And then in second question, by using a transfer function x and y and residue x and y and say pk z, the equation can be converted to get partial fraction value, which is here. You can get a partial fraction value. Then finally, for zpkx, using IOC plot, 0 and pole are able to be plotted on a graph. Then plot y is also used to plot the magnitude response, which is under question 3. We can clearly see. Okay. Then finally, on question 4 is how we manually calculate Laplace into reverse Laplace, or vice versa can be done too, which is under question 1, which has simplified the method on how we're going to calculate the Laplace and inverse Laplace easily without actually having to use paper and pen. This one is faster than the traditional method of calculating like this. And then, in conclusion, Laplace is able to do Laplace and inverse Laplace calculation, and then secondly, able to convert partial fraction using transfer function to get a partial function expansion. And then finally, it can plot 0 and poles and the magnitude system for us to see. Okay, that's all from me on Lab 4 in Laplace transformation. Thank you.